I generally call it a ski problem, but the way I draw it makes it more like a snowboarding problem. It's however you want to do it, I guess. Yeah. I'm gonna stick with my classic stick figure on something. The initial speed is approximately 0 meters per second. Right now, he's very delicately balanced, and that lands on his back, which is enough to get him to start moving. But his initial speed is close enough to 0 for our purposes. The reason why ski slopes are so popular in physics problems is the fact that you're basically sliding on ice. The coefficient of friction is close enough to 0 for us. So the coefficient of friction, he's going to be sliding, is close enough to 0. Now, recognize that weight is acting down on him the entire time. There's no friction, there's no tension, there's no other, because once the net lands on his back, that's it. We don't care about the net anymore. Normal force is also acting, but normal force is always perpendicular to the surface. So normal force is going to be acting like this, and then it's going to sort of keep changing direction as we go. So his acceleration is not constant, because weight's acting down the entire time, but the normal force is constantly changing direction, so the net force is changing, therefore acceleration changes. So let's take a look at him when he's at this spot right here. So we're going to do a force diagram on him when he's at that moment. Weight is acting down, normal force is acting perpendicular. Just like voxel ramp. So we have a conservative force, W, and we have a non-conservative force, Y. But the question is not whether we have a non-conservative force, the question is, does it do any work? At this moment in time, in which direction is he moving? Okay, I think, was that your answer, Amy?
I want to say down, but I'm not sure.
Technically, when you say down, that's like that. Okay, yeah, he's moving that way. You're absolutely right. Which way is the normal force acting at that moment?
Perpendicular?
Yes, they are, and therefore, what is the work done when the force is perpendicular to the movement? Greg, I think your head gestures are indicating it, but say it out loud.
0, nothing.
Absolutely.
Nothing.
So there is a non-conservative force here, but it's not doing any work, because it is always perpendicular to the movement. So, the work non-conservative is equal to the change in energy, and I'm not quite sure orange is really the best color here. See if this will show up with some zest. So, in the first case, non-conservative work was equal to 0 because we had no non-conservative forces. Now, the work done by the normal force is 0 because the normal force is perpendicular to the displacement. Basically, instantaneous displacement. The movement at that moment. And so we're left with this work non-conservative equals change in energy, therefore 0 is equal to E final minus E initial. Therefore, E initial is equal to E final. K initial plus U initial is equal to K final plus U final. Here we go again. Ready for unison. Chorus of angels. What's the formula for kinetic energy?
1/2 mv squared.
There. More enthusiasm too. Because physics only gets more exciting. Well, we'll jump past the first question and go straight to, what's the potential energy associated with this conservative force? With that conservative force.
Repeat the question, I'm sorry.
What is the potential energy formula associated with that conservative force? Yep, the only one we've really dealt with so far. It's equal to 1/2 mv final squared plus mgh final. This looks identical to where we were with that rock falling problem. And I'm just gonna write that 2 so it looks more like a 2. Is any of this, we have 4 terms here, are any of them equal to 0?
Yeah, V initial.
Yep. Close enough to count. At 0 because V initial equals 0 meters per second. Anything else equal to 0? Assume his mass is not 0. Assume that he's on some planet, so little g is not 0. So that basically leaves HI, VF, and HF. I guess let me state the problem. How fast is he going down here? That's what I want to know. There was one piece of information here I did not give you. So let's say he starts out a height of 50 meters above whatever that is. Okay, so people aren't sure. Can I get rid of any factor? I have 3 terms. Is there a common factor to all of them?
M.
Okay, so I can divide both sides by m, which is one of the reasons I did not give the mass. That was not an oversight. So I have GHI equals 1/2 mVF squared. Oops, not the m, I got rid of that. 1/2 VF squared plus GHF. All right, we're just ready to plug in numbers. Let's assume Earth, because it's a well-known fact that the only planet in the entire universe where you can actually do skiing or snowboarding is Earth. I defy you to find one bit of reference that any other planet hasn't. All right, so G.
Wait.
HI,
50.
what assumption did you just make?
Well, then you start at top.
That's not the assumption. Well, I guess it is an assumption. Yes, that is, I think it's part of the problem itself.
That's my assumption, I guess.
What?
That's my assumption.
We can
Okay.
make, we can make zero anywhere, so let's make
Yes, we
zero
can.
right there.
That's why before I said, is anything else equal to 0? Yes, if you want it to
If
be.
you want it to be.
If you don't, we can make it more difficult, but sure. So when you say the initial height is 50 meters, what assumption did you make besides the fact that the problem is true?
That the final height is 0?
Yes, height is equal to 0 down here. That is 0 because we say so. It is not 0 because that's the bottom of the problem. It's 0 because we're gonna say, hey, let's make that 0. You have the power to do this. So 50 is equal to 1/2 VF squared. And so 490 is equal to 1/2 VF squared. 980 is equal to VF squared. And so VF 31.3, 31.2. 3.
Meters per second. Meters per second.
That was my whatever units was. If you can see my mouth, that would have been much more obvious.
Maybe one day.
Yeah. It's nice to go a week without having to put a mask on. All right, so that's how fast he's going. Questions up to here before I change the problem slightly? All right, so he goes all the way down to the bottom. He's going about 65 miles an hour when he gets to the bottom of the slope. But he doesn't realize that there's been a cave-in. There's now a gaping hole there. He goes back up to the top, completely oblivious to the hole here, and he starts skiing down. And so he gets to this point right here, and then,
Splat.
now if you were concerned, at the bottom of this cave-in are clouds and cotton balls and kittens. Now he doesn't land on any kittens. If it had been cats, he would have landed on them and who would have cared. But they're kittens and they're too cute, so we don't hurt kittens. Kittens are there just to sort of revive him when he gets, after he hits. How fast is he going when he gets to there? I think some of you think you know the answer, and you should probably just say it.
The same.
Yes.
31.3 meters per second.
Absolutely. The velocities are not the same, but we have not solved for velocity, we solve for speed. The speeds are the same. If you think about it, the only difference between here and here is that here I have a normal force, here I don't. But the normal force isn't doing any work anyway. So none of this changes. The only possible place you can make a change is, assuming we still ignore air resistance, is if you want to make h equal to 0 some other place. If you want, you don't have to. Probably not worth the effort. So exact same speed. Questions to here? All right. Now, it turns out, the kitten showed him a way, that there's a series of steps inside this part of the mountain, and he makes it back up to the top. While he's working his way back up, it snows and fills in again. So this is now covered, he's not gonna fall that way anymore. However, as ski slope operators are prone to do, a giant spring was installed down here. giant spring. So he's gonna come down here, he's gonna be going 31.3 meters per second. At this point, he's gonna hit the spring and the spring's gonna compress. Now, I'm gonna make an assumption here, it is ideal. In other words, it's not gonna interfere with itself. As you know, if it were ideal, at some point, for example, it'd be very difficult to compress this any more than it already is because the coils get in the way of other coils. Or slinkies. Slinkies do compress, but they don't, I can't take the top of it and have it go all the way through the middle. At least not in classical physics. Now, when you're talking about springs, how much this compresses does depend upon what's known as the stiffness constant. And it's symbolized by a lowercase k. Generally called the spring constant. And it would be something along the lines of something newtons per meter. How many newtons does it take to stretch it a meter or compress it a meter? If it's ideal, it'll be the same either way. So I'm just going to say 40 newtons per meter. It takes 40 newtons to compress this spring 1 meter. It takes 80 newtons to compress it 2 meters. 120 newtons to compress it 3 meters. And so on. This we will get into much more detail near the end of the course in about a month. But for right now, it is a constant that tells us how stiff the spring is. How easy is it to stretch or compress? The force from a ideal spring is conservative. The potential energy, the force from an ideal spring, negative k delta x. The negative just means that the force is opposite the displacement. So if I compress it, the force the spring exerts is opposite that. If I stretch a spring, the force that the spring exerts is opposite that. So that negative sign is just saying it's opposite. Because it is conservative force, there's a potential energy formula. And the potential energy formula for an ideal spring is 1/2 k delta x squared. And I just sort of give this to you at this point as a gift. Derivation, we'll get to it. So, again, there is no non-conservative work. The normal force doesn't do any work. That still holds true. The only other forces involved are weight, which is conservative, and the force from the spring, which is also conservative. So this is the point where it changes. And I do need to give you a mass. We'll give him a mass of 70 kilograms. So the question is, how much will the spring compress? So we now have two conservative forces involved in this problem. So we'll have two potential energy formulas. All right, so kinetic energy,
1/2 mv squared.
like a single voice, awesome. mv initial squared plus the potential energy formula associated with weight. And the potential energy formula associated with an ideal spring.
1/2 k times displacement squared.
Or distance compressed squared.
Yep.
Yep. So 1/2 little k delta x. Actually, I'm going to throw in an intermediate stuff. You don't have to do this since you've already started it, but I'm just going to throw in this is kinetic initial plus use of g initial plus use of s initial is equal to k final plus use of g final plus use of f. Sorry, not f. S
Yes.
final. And then back to where I was. So that's 1/2 mv initial squared plus mgh initial, plus 1/2 little k delta x initial squared is equal to 1/2 mv final squared plus mgh final plus 1/2 k delta x final squared. Again, as you get more comfortable, there are a whole bunch of these steps that can be skipped, but until you're there, please go. So problem starts with him up there, it ends with the spring compressed, whatever that maximum compression is. What is equal to 0?
Initial velocity.
True. Or more specifically to this case,
Height.
so not velocity, but
Speed.
speed. Velocity is correct, but speed, again, trying to emphasize the fact that we're not dealing with vectors here. All right, so this is 0 because the initial speed is 0. All right, what else is going to be equal to 0?
Final height,
Why?
because we can.
Because he said so.
In this case, because Ian says so. All right. We got a couple more that we can make 0. Or a couple more that will be 0. Let's see, we got four terms left, so. Take it step by step. Is the initial potential energy 0? In other words, is M0, G0, or H sub I 0?
No.
All right. We had our chance to make H sub I equal to 0, but Ian beat you to it. All right, so that's not 0. What about here? K is a constant related to a spring, a specific spring, that one. 1/2, I'm just gonna go out there and just let you know 1/2 is not equal to 0. I hope that doesn't rock your world or certainly shake the foundation of everything you knew. The initial displacement of the spring, is that 0 or not?
Yes.
Yes.
Yeah, because it's just sitting right there. All right, and then we're down to the kinetic final kinetic energy. Again, 1/2, not 0. The mass, not 0. Final speed, is that 0?
Yes.
Why?
Because you're just doing it to when the spring's compressed, right?
Right?
So your final displacement's gonna be 0. I mean,
You said all the parts.
I know. I'm trying to get it straight in my head.
I'll give you a moment. Or someone else wants to chime in.
I agree with what he's going with, because like he was saying, you only care about how much the spring is
Compressed.
compressing, and
And
the
this will
speed
end.
after that doesn't matter.
Okay. If the speed were not zero, that means he's still moving, which means the spring is still
Spring's
compressing
not
more.
compressed.
Yeah.
Right, yeah.
All right, so this is, no, sorry, this one. That is zero because we're at maximum compression. And those were that's supposed to be English letters. Maximum compression, I'll abbreviate at that point because it's getting worse and worse. So what we've done is we started out with a very simple equation here, and we made it far more complex, and now we're down to specifics to this problem, which simplifies it even more. And so what I'm left with is mgh, the initial, is equal to 1/2 k delta x final squared. That's what it's come down to. All the potential energy we have at the beginning eventually gets converted into potential energy of the spring.
Oh my, that was loud.
Bless you.
Thank you.
So here's the visual, the hand gestures. We start out with all this gravitational potential and no kinetic. As he's going down the slope, as we lose gravitational potential, we gain kinetic. And so total energy stays the same. Then once he's at the bottom, it's all kinetic and no elastic potential. The spring potential would have been, calling it officially, it's elastic potential. And then as he gets into the spring, he starts slowing down and the spring starts compressing. And so all that kinetic energy gets converted back into potential energy, this time elastic potential. So we start out with all gravitational potential, we end with all elastic potential. So my initial potential here is equal to my final potential here. The kinetic energy, there is this intermediate step, but ultimately, since there's no loss of energy, we can skip it. So now it's plug and chug time. And so I have 70 times 9.8 times 50 is equal to 1/2 times 40 times delta x final squared. And I'll go to side by 20. So around 1700. 1715.
And the square root of that would be 41.41. Since that's displacement, would that be meters?
It would be. So the spring gets compressed, basically half a football field.
Big spring.
It is. But, you know, ski slopes do not spare any expense when buying springs at the bottom. All right, so the spring is now compressed 41.41 meters, and of course, it doesn't stay that way. It then launches and it gets shot back. Again, we're assuming frictionless. We'll assume that the back ends of the board or skis does not dig into the snow. How far back up the hill will it go? And I'm betting some of you've got a gut feeling what the answer is. Just go for it.
41.41 meters.
No. Wrong gun.
Wrong good.
Would he make it right back where he started since energy's
Ah,
Yes.
geez, that's right.
That's where he
You
fell.
just told us
Where
that.
it took to go up.
So think about that. If he's on his way back up, we're no air resistance, but suddenly as he's going backwards and that lands on his chest, that's just a tiny bit of energy would be enough to send him back down over here. Now, he's not going particularly fast at that point, but he would go back and then he'd get to the bottom here going 31.3 meters per second.
Yep.
And that's the ski problem. It's just conservation of energy. Are there questions? All right. Is it helpful for me to do a really complicated problem just to show you what the worst looks like? Or does it just freak you out too much?
You're gonna put it on a test?
You know, I problem I was about to show you is one that has been on a test before.
Then yeah, we'd like to see it.
That, yes, also, everyone else just sort of gonna go with the flow.
You just want to freak us out.
It's not my intent, my intent is to, you know, like G. Gordon Liddy, he was scared of thunderstorms, so he went up in the tree during a lightning storm just to get over his fear. Some might call it insane, and some might call it how to face your fears. So I was hoping to basically put you in front of a lightning storm here. Actually, is G. Gordon Liddy dead? Or is he still around? Yeah.
I don't know.
I heard him speak when I was at Duke, and he was one of the masterminds behind the Watergate break-in, for those who don't know who G. Gordon Liddy is. And he talked about sort of the global economic, or the global military situation. And there were two professors who were gonna ask him questions before they allowed the audience to ask questions. And the first one asked him about exactly what he talked about. And the second one got up there and he said, the last time I was in front of on a panel like this, I was trying to justify showing pornography at Duke. I feel exactly the same way now. And at which point G. Gordon Liddy laughed. And then the question was, how do you justify the illegal things that you did? Anyway, just a little vignette from my past.
He's still alive.
He is still? Okay.
He's 90.
90? I don't know if you've noticed, but over the past year, I don't know if I mentioned this class, but it seems like somebody has something out for the people who are 90 years old and older. Because there have been a whole bunch of them that died this year.
They have.
And then they had an 88-year-old the other day, so I'm thinking.
They're getting younger.
Yeah.
Shoot.
All right. The scary conservation